Students, good morning. Today I am going to solve one more problem. The problem comes under the category of application of thermodynamics to flow process. Applications of thermodynamics to flow process. The problem is carbon dioxide is to be compressed from a given pressure to exit pressure. The problem says that carbon dioxide at 1 bar and 300 degree Kelvin is to be compressed adiabatically to a pressure of 10 bar. So initial pressure, inlet pressure is 1 bar, exit pressure is 10 bar. Inlet temperature is 300 degree Kelvin. Final temperature is not given in your question paper. At a rate of 100 meter cube per hour, mass volumetric flow rate of carbon dioxide is given 100 meter cube per hour. So inlet condition P1 is equal to 1 bar. 1 bar is nothing but 1 lakh Newton per meter square. Similarly, exit pressure is 10 bar. 10 bar is equal to 10 lakhs Newton per meter square. Inlet temperature P1 is equal to 300 degree Kelvin. Exit temperature P2 is unknown. Volumetric flow rate of carbon dioxide is given 100 kg per hour. So into 3 divided by 3600 seconds into 1 hour. Hour gets cancelled. 100 divided by 3600 is equal to 100 divided by 3600 0.0278 kg per second. This is the metric cube per hour. Okay, this is metric cube per hour. This is metric cube per second. So volumetric flow is given. Density of carbon dioxide CO2. Density of carbon dioxide at 300 degree Kelvin is 1.78 kg per meter cube. So this volumetric flow rate can be converted into mass flow rate by multiplying the density. Mass flow rate of carbon dioxide is equal to volumetric flow rate into its density. 0.0278 into 1.78. The answer becomes into 1.78 0.049 0.0494 kg per second. Okay, now I am going to find the exit temperature. In order to find the final temperature, you should know the temperature pressure volume relationship for an adiabatic process. In an adiabatic process, PV power gamma is equal to constant. Similarly, T V power gamma minus 1 is equal to constant. Moreover, T power gamma into P power 1 minus gamma is equal to constant. This is the relationship, temperature pressure relationship what we want to find the final temperature. From this relationship, temperature P power or temperature power gamma is equal to P power gamma minus 1. So temperature is equal to pressure power gamma minus 1 divided by gamma. So T2 divided by T1 is equal to P2 divided by P1 power gamma minus 1 divided by gamma. So final temperature T2 is equal to T1 into P2 divided by P1 power gamma minus 1 divided by gamma. So initial temperature 300 degree Kelvin into 10 divided by 1 to the power of 1.3 minus 1 divided by 1.3. The answer becomes 510 degree Kelvin. So the final temperature is 510 degree Kelvin. It was established using the temperature pressure relationship of an adiabatic process. So T2 is equal to 510 degree Kelvin. Now the final temperature was established. I am going to find the compression work required for compression from 1 bar to 10 bar. WS. Yes, right? First law of thermodynamics. First law of thermodynamics to flow process. Flow process is half m del v square plus m g del h plus changes in enthalpy is equal to q minus shaft work. In most of the flow process, contribution by kinetic energy and contribution by potential energy are assumed to be zero. The process is adiabatic. Adiabatic means changes in heat content is zero. That means dq is equal to zero. Heat content of the system is constant. Hence, q term gets removed from the equation. The leftover part minus w is equal to del h, changes in enthalpy. Listen, it is a reversible adiabatic process. Adiabatic process means there is no exchange of heat between system and surrounding. Reversible means the amount of work supplied to the compressor to compress the gas from initial pressure to final pressure was completely replaced. It is a reversible process. In reversible process, changes in entropy is zero. Changes in entropy is zero for reversible process. Hence, it is isentropic process. Hence, I use the notation S. This S stands for entropy is constant. Entropy is constant. Isentropic process. In isentropic process, the shaft work is called as isentropic work. Isentropic work. Isentropic work means this is the minimum amount of work required for the compressor to compress carbon dioxide from 1 bar to 10 bar. It is the minimum amount of work required for the compressor to compress the gas from initial initial pressure to the final exit pressure. Okay, right. This is the equation we want required to find the amount of work done. So W S shaft work is equal to minus del H S. This is Cp into dt. Changes in enthalpy is equal to Cp into dt. Cp is nothing but gamma divided by gamma minus 1 into R. This is changes in temperature, final temperature to initial temperature, minus sign. In order to remove the minus sign, gamma divided by gamma minus 1 into R into T1 minus T2. Clear? This is the equation to estimate the amount of work required. Ws is equal to gamma 1.3 divided by 1.3 minus 1 into 8.314 joules per mole degree Kelvin into initial temperature 300 degree Kelvin minus final temperature 510 degree Kelvin. Kelvin gets cancelled. The remaining answer is joule per mole. Joule per mole. What is the answer? Minus 7565 joules per mole. This is the amount of energy required to compress the carbon dioxide from 1 bar to 10 bar. Thank you.